Today I'm going to talk about double integrals over rectangles. We have done derivatives, we've done limits, we've done max-min or optimization problems, we've done related rates. Finally, it's time to do integrals. So let's remind ourselves what integrals are from Calc 2. Remember we had an average Joe curve. We wanted to find the area under the curves. We drew in a bunch of rectangles, and the sum of the area of the rectangles approximates the area under the curve. So AI represents the actual area under the curve, and it's approximately equal to f of xi star delta x. Each of these subintervals has a random point, xi star, and delta x would be the width of this mini interval. If I wanted to find the area under the entire curve, I would just add up these AIs, and that's approximately the area under the curve. And if I wanted to find the exact value, I wanted to make these rectangles smaller and smaller. So I would take the limit as n goes to infinity. And then we define the integral from a to b, whatever our region is, to be that limit. So how does this transfer into 3 space? So this time I have a region from 0 to 2, 0 to 3. I have a rectangular region. I want to find the volume. So I'm going to chop up my rectangle into smaller rectangles. And then we're going to chop them up into smaller squares, etc. Now let's zoom in on one of these squares. I have the rectangular region AB cross CD, and I'm going to chop it up into a bunch of smaller rectangles. And this is one of those rectangles. My AB interval is chopped into M pieces, xi to xm, and my CD will be chopped up into N pieces, so I have yi through yn, meaning I have M times N rectangles. And this is just one of them. The area of this rectangle is based on the width and the height. The width goes from xi minus 1 to xi, which is our delta x. And the height goes from yj minus 1 to yj, and this is my delta y. So the area is delta x times delta y. So we label this area delta A. And just as I chose a random x star in each interval, I'm going to choose a random point in my rectangle and label it xi star yj star. So now I need a little bit more room. Go to the next slide, squish everything up. The approximate volume in this region will be f of that point times the area of A. If I want to find the approximate volume under the entire surface, I add them all up. The more rectangles, the better the approximation. So I'll be taking the limit as both m and n go to infinity to get the exact volume. And this should look familiar, that obnoxious limit of summation that you had in Calc 2 when you first defined what an integral was. And this we denote as a double integral over d of f of xy dA. Time for an example. Let's say we have the function x squared y minus xy squared plus 10. That looks like this. The region I care about is, I'm going to let x go from 0 to 2 and y go from 0 to 3. I have the integral from 0 to 3, integral from 0 to 2 of my function dx dy. The integral from 0 to 2 matches up with the dx. The integral from 0 to 3 matches up with the dy. They're like parentheses. To kind of get a better feel for what I'm doing, give myself parentheses so it looks easier. It looks something like this. On the left is how I would do it if I did x first, but I can just as easily do it with the y first. The nice thing is if you're doing this over a rectangle, order doesn't matter. So I need more room again. So here's my integral. I'm going to work on from the inside out. Integrating this, I get x cubed y over 3 minus x squared y cubed over 2 plus 10x. I need to take this as x goes from 0 to 2. First plug in my 2, subtract my 0 when I plug it in, simplify, and I get this. Now this is an average Joe polynomial. I can integrate with respect to y, and then plug in my 3, subtract my 0, simplify. 31.5. So that means since my function was positive everywhere, this is the volume under that surface, between the surface and the xy plane. Let's look at another one that's a little bit trickier. Here we have y sine of xy. I want my x to go between 1 and 2, and my y to go between 0 and pi. This function looks like this. Notice I have some negative parts of this, so they're going to cancel out with the positive parts. Let's see what we get. I can also write this d using interval notation. I can say 1, 2 cross with 0 pi. Now let's look at this integral. Writing it generically, I have to decide, do I want to integrate with respect to x first or with respect to y first? I'm going to integrate with respect to x first because doing it this way, I can just do it by substitution. So this is a constant sine of a constant times 3 dx. Well, if that constant were, say, a 3, let's go over here and look at this. If I had 3 sine of 3x dx, that's easy. It's just negative cosine of 3x. You're undoing the chain rule there, plus c. So I'm going to choose to do it that way first. So integrating this, I get negative cosine of xy, and the x goes from 1 to 2. Plug that in. Now I have this to integrate. Integrating again, I get this. If I plug in pi, I will get 0. If I plug in 0, I will get 0 because sine of 0 is 0, and sine of pi is 0, sine of 2 pi is 0. Well, how unfortunate, the answer is 0. That means the volume above the plane is the same as the volume below the plane. Let's try another one. In this one, I want to integrate x e to the xy dA, where r is 0, 1, cross 0, natural log of 5. I have to decide which way to integrate first. Well, if I integrate this with respect to x, I would have to do by parts. And the 3 just is standing for the y, to emphasize that the y is a constant. I just threw in a 3 to be the constant. If I integrate it with respect to y, then it's just a baby substitution. So I choose to integrate with respect to y first because it's easier. So integrating from 0 to natural log of 5 of x e to the xy dy, I do the inside first. Integrating that, I get e to the xy taken from 0 to natural log of 5. Plug in what I need to plug in. E to the 0 is 1, that's nice. E to the x, natural log of 5. Wait, what's that? Okay, let's simplify that first. Let's go over to the right and see what e to the x, natural log of 5 is. It's the same as e to the natural log of 5 to the x. Well, e to the natural log of crap is crap. So I'm integrating from 0 to 1 of 5 to the x minus 1 dx. And I need space. Well, if I need to integrate 5 to the x, we recall, of course you recall, that the derivative of 5 to the x is 5 to the x natural log of 5. So going backwards, if I integrate, the integral of 5 to the x is 5 to the x over natural log of 5. So integrating, I get 5 to the x over natural log of 5 minus x. I plug in a 1, then I plug in a 0, and I get 5 over natural log of 5 minus 1 over natural log of 5, which simplifies to just 4 over natural log of 5 minus 1. So this is the actual volume under the surface. So what are our takeaways? You know how to integrate. You've done it before. And we're not going to get into the really gross ones that you may have seen in Calc 2. Check to see if it is easier to integrate with respect to x or y, and do it that way. And then integrate. So it's pretty straightforward. It's not really new. It's just a different way of looking at it. So good luck.